Welcome. I'm Randy Osborne. You're listening to the Bible Science for Kids podcast from a uniquely young earth, biblical creationist perspective. This is Cycle 2, Lesson number 21, the third law of thermodynamics. But before we start today's lesson, let's do a quick review of our last lesson. Do you remember what is the second law of thermodynamics? Answer: the second law of thermodynamics, often called the law of entropy, explains why heat flows from an area of higher temperature to an area of lower temperature. The second law of thermodynamics tells us that energy naturally spreads out and that things fall apart over time. Remember the concept of entropy, symbolized by a capital S? Entropy means that energy or matter are disordered, mixed up, randomized, or spread out. The universal law of entropy, the second law of thermodynamics, helps explain everyday events like death and decay. It is a difficult thing living in a cursed, fallen world. Remember that Jesus' resurrection from the dead shows us that he has the power to subject all things unto himself. He will never be subject to decay. Our God and Savior, Jesus Christ, is the same yesterday, today, and forever. Physical things decay and fall apart, but God is Spirit. Good job. Who's proud of you? I am. We are in Cycle 2. This is Lesson number 21, the third law of thermodynamics. What is temperature? Do you remember kinetic energy, the energy of motion? Temperature is simply a measure of the average kinetic energy of the particles of a substance. The faster that the atoms or molecules vibrate, the higher the temperature registers on a thermometer. The slower that the particles vibrate, the lower the temperature of the atoms or molecules. Cold means slow motion wiggling. So how does a thermometer know what temperature is? A thermometer is like, for example, the kind with the red liquid in a thin glass tube. It's measuring the volume of expansion, which is swelling, or contraction, which is shrinking, of alcohol molecules. So since alcohol's volume reliably changes with temperature, it's good to use in a thermometer. A person marks the tube when the pure water that the thermometer is touching freezes, and they mark the tube again when the pure water starts boiling. I say pure water because a very, very smart inventor and scientist named Daniel Gabriel Fahrenheit once marked the thermometer tube when the water was freezing, but it wasn't pure water. The water he had looked like normal water, but it was salt water. Salt water freezes at 0 degrees Fahrenheit, but he thought he was marking 0 degrees Fahrenheit for normal pure water. At least that little mistake taught us how to make the roads less slippery in the winter. Do you know how? When we salt the roads, snow and ice melts, making it much safer to drive. Let's listen to what God says to Job in Job 38, verse 22 of the New King James Version. Have you entered the treasury of snow, or have you seen the treasury of hail? Question: what is the third law of thermodynamics? Answer: the third law of thermodynamics explains that it is impossible to reach the state of absolute zero temperature. If temperature represents the moving of the little particles of things, and fast is hot, and slow moving is cold, then how cold would something have to be to get as cold as possible? So cold that all movement stopped. That's what the third law of thermodynamics is all about. It helps scientists understand what happens to matter and energy at extremely low temperatures. While we don't see this law in action every day, it teaches us important truths about the limits of nature and how even science points to a world and a universe with boundaries, with laws, with limits. These natural limits were not some random occurrence of chance, but they were intentionally created and established by God. God even gave a limit to the sea. He only lets it come so far. The third law of thermodynamics was developed in the early 1900s. A German scientist named Walther Nernst proposed it around 1906 while studying how substances behave at very cold temperatures. He worked in Germany, and he wanted to understand how energy and chemical reactions work near a temperature called absolute zero. This helped scientists complete the bigger picture of how energy behaves, and it earned Nernst a Nobel Prize in Chemistry in 1920. Remember the name William Thomson, also known as Lord Kelvin? Using mathematics, he figured out that the theoretically coldest temperature on Daniel Gabriel Fahrenheit's thermometer scale was negative 459.67. That's 459 and 67 hundredths of a degree Fahrenheit. Anders Celsius redid the temperature scale to make it more useful for scientists. Instead of ice water freezing at 0 degrees, he made a scale where fresh water froze at 0 degrees. He also marked the boiling point of fresh water at 100 degrees, a nice round number, instead of 212 degrees Fahrenheit. So the tubes are the same, just the markings and the numbers are different on those two temperature scales. But even this scientific scale had a strange number for Kelvin's coldest theoretical temperature. Celsius's scale showed negative 273 and 15 hundredths of a degree Celsius. Negative numbers for absolute zero. So Kelvin made his own scale, the Kelvin scale. And his zero really is zero. Zero motion of the particles. No wiggling, no vibrating of the atoms or molecules at all. This is what absolute zero, 0 kelvins, means. Nothing in nature ever quite reaches absolute zero, where the vibrating motion of all atoms and molecules completely stops, because the number of steps it would take and the amount of time it would need seems to be infinite. But here's how we try to make it happen. Number 1, compression of gas followed by expansion of that gas. Why? Did you ever spray something from an aerosol spray can like shaving cream or hairspray or spray paint and then feel the can? The can suddenly feels very cold. That's because it is the hottest and most energetic molecules that leave the can first, leaving the colder ones behind. It reminds me of adiabatic cooling. You feel it when you're walking outdoors and suddenly there's a cool breeze, and then soon it starts to rain. Let me tell you why it feels cool, and then have you do a demonstration using your own breath. A birthday cake with many lit candles on it would show an extremely hot temperature if you used a thermometer in the middle of all those candles. But don't do it because you'll break the thermometer. The temperature reading on that thermometer represents the average kinetic energy of all the molecules of that hot air. But if you were to keep the lit candles, all of them, but just simply spread them out, spread them apart equally in the room, the thermometer will show a much lower temperature, even though the same heat is all in the same room. So why will it show such a lower temperature? Because the heat's all spread out. The average molecule of air that's touching the thermometer is much cooler. Now to demonstrate adiabatic cooling with your own breath, put the back side of your hand near your mouth, not your palm, the back side of your hand, just an inch or two away. Open your mouth and slowly breathe out. See how hot it feels? Now, try this. Same body, same breath, same distance to the back of your hand, but instead of opening your mouth wide, pretend you are blowing bubbles through a straw. See how cold it feels? Same body, same heat, same air, but it feels cool now because the air molecules of your breath are expanding far apart when they come out of your lips. Like the hot candles, spread out far apart and felt cooler in between them. You're putting space between the hot molecules by pushing them apart. Second, Doppler cooling is the second method they use to supercool molecules. When laser beams from all sides hit molecules at the same time, it can slow them down, which cools them. Third, they use evaporative cooling, which means that when placed in an optical trap, the hottest, most energetic molecules can be allowed to escape the trap, leaving the coldest ones behind. Fourthly, fields of magnetism can hold atoms in place by magnetic levitation, so they're not even touching something that could conduct heat to them. And fifthly, gas pressure lowering. Using suction of a vacuum pump, they can promote extra evaporation and keep carrying the hottest molecules and atoms away, 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 so that only the coldest ones remain. Do you see how knowing the behavior of matter and energy can help you to direct matter and energy to do what you want to accomplish? You may wonder about how cold the coldest known place in the universe is and where it is. The coldest naturally occurring temperature that we know of was measured in a dark cloud in space, 5,000 light years away from us, inside the Centaurus constellation, in a place called the Boomerang Nebula. A nebula, if you recall, is a dying star. Its temperature was measured at just 1 Kelvin. It's rapidly expanding, so it's adiabatically cooling, like an expanding, rising, low-temperature air mass, which quickly cools its gas. Astronomers couldn't touch a thermometer to a nebula, so how did they measure the temperature of the Boomerang Nebula? Astronomers used sub-millimeter telescopes to observe molecular carbon dioxide emission lines that are changing during extremely low temperatures. From these emissions, they infer the gas temperatures. The temperature is inferred from how the light looks. Question: what is the third law of thermodynamics? Answer: the third law of thermodynamics explains that it's impossible to reach the state of absolute zero temperature. Why? Because the number of steps it would take and the amount of time it would take seems to be infinite. Listen again to what God says to us in Job 38:22. Have you entered the treasury of snow, or have you seen the treasury of hail? Thank you for listening to the Bible Science for Kids podcast from a uniquely young earth biblical creationist perspective. I hope to see you next time for Cycle 2, Lesson number 22, Light. Until next time, this is Randy Osborne reminding you to keep trusting and serving the Lord. And don't forget to tell a friend. Remember to share good things with those you love. Who's my student? You are.